Hello, everybody. Welcome back to the Incubator and Neonatology Review. It is Thursday. Daphna, how are you?
I'm doing great. I'm so glad we're going to have some help today.
Yeah, we have a special episode. Rooney is in the studio today. Rooney, how are you?
I'm doing great, Ben. Good to hear your voice again, Daphna.
Mm-hmm.
We are enrolling the help of Rooney to go over some difficult concepts in cardiology. Rooney is our regional director. We work with him every day, and he was interviewed on one of the first episodes of the podcast if you want to find out more about him. But for those of you who don't know him, he is a neonatologist. He is a pediatric cardiologist. He is a cardiac intensivist. So he has the knowledge. He has the goods to help us understand cardiology. And so we've asked him to join us in helping us understand some of these concepts. So Rooney, what are you going to go over today with us?
I was thinking we'd start with cardiac embryology.
Yeah, that sounds great.
Yeah.
And so Rooney is in the studio. We're recording a video as well with slides and stuff that we'll post on our YouTube channel. So we'll have that content available on 2 platforms for people who are interested. Rooney, go take it away.
Yeah, that's great. Well, thanks so much. And also thanks for taking the slides and being able to show them, because a lot of this is obviously visual. But, truly an amazing process of creating and building a heart during embryology. It's beyond fascinating and endless, and you can continue to read and read and read about it. However, today we're going to focus a little bit more about the things that potentially could show up on the boards. And they're not a whole lot of questions on cardiac embryology on the boards, on the neonatology boards, but they do pop up. Often they might be kind of at the level of what's known as kind of tertiary level knowledge, where they might give you a patient kind of phenotype of a syndrome, and then they will kind of backtrack a little bit and say potentially what could have happened in embryology to result in a common heart defect as related to this syndrome, for example. So today we're just going to start talking about the big picture of cardiac embryology, and we can just start by saying that the first 2 weeks of life, humans really.
So you were saying in the first 2 weeks of life.
Yeah, so really during the first 2 weeks of life, humans have no heart and no vascular system because there's no need for it, right? And it's starting to develop. However, the formation of the heart starts very, very early in embryology. So if you kind of compare it to history, it's kind of ancient history as compared to modern history, where the lungs continue through from the medieval ages all the way up to modern history, whereas cardiac embryology is really ancient history from the beginning, and then it finishes. So the heart is fully formed and functional by 8 weeks gestation. And then we're going to start somewhat early, just so you understand kind of the very beginning. So gastralization is week 4. Which really starts with the formation of the germ layers. And then you have the epiderm, mesoderm, and endoderm. I'm not going to talk about this in detail, but the reason why this is important is that you have this, at some point, this gastralization at week 4, which really means that this entire thing kind of folds in on itself, so that it's kind of creates its own internal cavity. Mm-hmm. And that internal cavity has in the center a floor, if you will, or a disc, and that is known kind of as an embryonic disc. And this embryonic disc lies on top of the yolk sac, so it has tons of nutrients that actually come up from it. So it's like having the best fertilizer, if you will, to really just use any kind of nutrients for further development. So once you have this embryonic disc, you start having small buildups of cells. And at this stage, you have kind of a ventral and dorsal organization, but you don't have a left and right form of differentiation. In the middle of this embryonic disc, there's a little streak called the primitive streak. And it's part of this kind of direct area of the crescent. You start having a unique development where these cilia start growing up like little kind of buds coming up like seeds almost. And these really start developing a form of movement. And I guess, as far as I can imagine, this is really when the first activity, a kind of cell movement in that area, and these and a rhythm in many ways. So once you start,
that's why we're seeing a picture of the mariachi band.
Exactly, because that's where the rhythm starts, right?
Okay.
So,
are you a fan of mariachi?
Well, who can't love that kind of music?
I know. I went to Mexico not too long ago. It was so good.
Yeah. Every now and then when I'm on call, I need a little pick me up. Yeah. But anyway, so as part of this primitive node and the cilia that starts growing up there, these cilia start in a kind of vortical type movement, almost like a tornado type movement, and it's counterclockwise. Okay. And again, so these cilia coming up so early in embryogenesis, and in the center of the in the primitive node of this crescent is the beginning of your left and right differentiation. And in cardiac embryology, as in your entire body also, but specifically in cardiac embryology, left and right differentiation matter. As we all know, there's a big difference between your left side of the heart and your right side of the heart. And that is one of the reasons why a lot of your kind of orientation in space from the left to right side is based on the findings of the heart. And really the kind of the go-to part of the heart is really the atria. So you can really define the difference between the left atrium and the right atrium. And as a cardiologist, that's kind of what you go to primarily to define the left-sided structure or right-sided structure in the heart. Anyway, the beating of the cilia really causes mostly a leftward flow of fluid across the embryonic disc. Okay. And as you have this leftward flow of fluid, you have a movement of certain hormones and genes and everything in one direction. Very quickly, the primary the cilia are structured like this, and primary ciliary dyskinesia or Cartaginer syndrome is kind of the classic poster child for left-right differentiation. However, there are a lot of kind of other forms of left-right differentiation problems that are not necessarily related to primary ciliary dyskinesia, but there have been several questions on the boards that actually look at primary ciliary dyskinesia or Cartaginer syndrome in babies who may have respiratory symptoms at birth, and or have family members who have frequent sinusitis problems, and then they might ask a question like, is this baby at increased risk of, say, atrial arrhythmias, for example, which it would be, for example. So anyway, so that's kind of, again, tertiary knowledge that kind of tied into this aspect of embryology. And on this slide 12, there's again, kind of shows the relationship between the yolk sac, the primitive streak in the center where the cilia come up, the amniotic sac, and how you're kind of embedded within the amniotic sac, and you have the cilia, then they're moving and doing their thing, and starting to create a cell differentiation at the level of this embryonic disc, which then, as it's doing this and cells are starting to develop, you're creating kind of a almost a little bit of a hierarchy of cell or differentiation of cells. And that's when you end up into kind of the various heart fields. And the primary heart fields, the progenitor cells there really start leaving this primitive streak and start migrating mostly in the cranial and lateral direction. As they leave the primitive streak area, and this is again starting to differentiate cells over time. And we're going to talk a little bit about the various the heart fields and what they form over time. But again, this is the beginning of this differentiation as part of in the endoderm. And then at this stage, you start running out, as far as I understand, the nutrients that actually diffuse up from the yolk sac. So you're starting to actually have not only the genetic factors, but you also starting to have nutrients that start flowing on top of this in the heart field within this heart tube. We'll get back to that a little bit more. So let's get back to left-right differentiation, because it is important clinically. It is important for the boards. Again, I've said there's a gradient of signaling of molecules that kind of creates an asymmetrical development of the various organs. This starts early. So if there's a question, when does left-right differentiation start? It starts during gastrulation. And then they might ask what genes are part of the production of the left-right differentiation. There are several, but the node is known to secrete growth factor beta related proteins. And there are two genes, lefty 1 and lefty 2 genes, that act in an agonistic way. However, these genes tend to mostly be moved and transported to the left side.
For once, we have gene names
that makes sense,
that can be remembered. So lefty 1 and lefty 2 that act as agonists.
Exactly.
To transport material to the left side.
Exactly.
Of the That's great.
Yeah. So don't think that's like
that's one you would be able to pick out of the drop
Actually,
down
you would
menu.
probably not even pick this one, because you would say, no,
you'd be like, surely that's not a gene name.
Exactly. That's what I'm thinking. So I'm like, no, that's too simple. It can't be lefty 1 and lefty 2, right? But if they don't have lefty 1 or lefty 2 on there, know that PTX2 is the master gene for left-sidedness. Okay. So that's another good one to go to. And I do believe at some point there was a question or alluded to something that of serotonin. So there's a increased concentration of serotonin on the left side of the embryonic disc. Okay. So we're talking lefty 1, lefty 2. PTX2 is a master gene for left-sidedness, and serotonin is important for left-sided development. So again, obviously, it does become relatively complex here, but those are the kind of big points there. Moving down, kind of now we've created these heart fields, and what heart fields are really just kind of fields of cells that are starting to differentiate into what's going to become myocardial cells. Okay. Mm-hmm. And based on the genes that they're embedded in, they're going to act differently.
Right. Based on their milieu, basically.
Exactly. And it's going to also, their migration and proliferation of certain kind of sometimes referred to as cardiac neural crescent cells, which fall under kind of a notch pathway, kind of how they develop and how they grow. Okay. So as part of the, these hard fields, they kind of combine, and now you actually have a growth of the cells together, and they start ultimately resulting into kind of the famous heart tube. Okay. And in this heart tube, you partially have something known as the cardiac jello. And in the cardiac jello, you have these progenitor cells that ultimately going to become myocardial cells. However, what's unique, and then the question is, I guess they're not really a question of when the heart really starts beating, but the cells in this cardiac jello or jelly do start, they actually contract. But does the whole entire cardiac tube contract and move anything back and forth? Probably not at this stage, but the cells themselves have are kind of differentiated in such a way that they do start contracting.
But there's no synchrony, I guess.
No, exactly. So, and you actually have a left endocardial tube and a right endocardial tube. They fuse together, and then you have a one single cardiac tube. And this is, again, relatively high up in the embryo. And obviously, when we talk about this, we're talking tiny, tiny distances, right? We're talking almost micrometers in kind of how far these genes need to travel. And on this one slide, you kind of see how the cardiac tube looks at day 20, day 21, and day 22. Since this happens so quickly, there's, it must be fascinating to be a cardiac embryologist, because if you leave one of these in your kind of Petri dish or whatever, they leave them in overnight in a good environment, the next morning they're going to, have a very different heart to look at. Anyway, we talked about the heart fields and the cardiac tubing. So on this slide, it kind of shows you in a color system what the aspects of the cardiac fields, what they become moving forward.
Yeah, because it's very interesting, right? The first heart field template that you talk about, and I'm sorry, like this is very not medical, but it looks like an airplane pillow.
Yeah.
So it has these two little things, and then this is where basically you're going to have you have your ventricle, and this is where you're going to have your atria, and the atria are sort of the two endpoints of that little airline pillow.
Exactly.
And so what's interesting is that the atrium are kind of looking like they're at the bottom, and they're going to sort of circle back to the top.
Be on the top.
Yeah,
exactly. And that's kind of how, if you look at the tube again, the right and the left sinus venosus and the atria, so they're connected. But the atria that we're talking about here are the primitive atria. And the primitive atria ultimately end up being the appendages. Yeah. And so here, the atria that we're talking about here in the cardiac tube are going to be the appendages. And those are the ones that we use from an echo standpoint to really define left and right side.
Right.
A large part of the atria in a formed heart is part of the venous system. So the sinus venosus really on the right side, right atrium, and something called a dorsal mesenchymal protrusion in the left atrium. But we'll get there. So when it comes to the primary heart field will form the left ventricle, the kind of upper parts of the atria, and a small part of the right ventricle. So they might actually, these questions do occur on the boards. What the primary the heart fields turn into, and the secondary heart field will constitute the rest of the right ventricle, both outflow tracts, because the outflow tracts both come from the truncus or the conotruncal region. And the secondary heart field also does the caudal part of the atria. So we talked about kind of these type of regulations, but now we kind of fast forward relatively quickly. But obviously, this takes, doesn't happen immediately, and these heart fields form over time. There are a couple of other genes that I just wanted to throw out there that's important for you to add in your notes. And these are kind of regulatory genes as part of cardiac development. The NKX 2.5. It's something that, honestly, if you read it in a textbook, I would skip over it, right? But it is considered the master gene for cardiac development. So it's important to know this. The TBX5 is important role in septation. And that's a question that could pop up. We talked about lefty 1 and 2. There's also something called hand 1 and hand 2, which plays a role when it comes to cardiac looping.
Yeah, that's another one that's easy to remember.
Yeah. Okay. Very good. So, other important regulatory cardiac developments, again, I think is important to just say them. Sonic Hodge regulates secondary heart field and plays a role in outflow tract formation. Notch 1 is an important part as part of the JAG system. And this is when we do the kind of aspect of the genetic part of cardiology. It's Alagille syndrome. It's kind of the poster chart for Notch 1 and JAG 1, and they tend to have can have any form of cardiac disease, but frequent VSDs of pulmonary arterial stenosis at any level. So I think these are high yield genes to note as part of cardiac development.
Okay, Rooney. I think you have more to tell us, but we're gonna pause here for today. Daphna, do you have a question for us? All right, you're muted. It's good when the person who gets frustrated that they're muted is sort of cursing, but they're still muted.
Yeah. I need that.
Oh, gosh. Okay, I have a few questions on cardiac development, but
We'll do one today, and then we'll have more for tomorrow.
that's what we'll do. Okay. Bear with me. Now I moved everything around. It's coming. Sorry, my book is thinking. Oh, man.
Actually, I brought that question. Sorry, but it was from 2017 or something.
No worries. Let's just hope Daphna can find the question.
Yeah. Was that an okay? I can talk, right? Because you got to cut this out.
Mm-hmm.
Yeah. Right?
Yeah, the questions that are in the board review book are super basic. That's all. Just wanted you guys to know that. And you didn't quite get to the arches yet. I have this one on conotruncal development and endocardial cushions, and one on heterotaxy.
Okay. Because that's actually interesting in relation to atrial septation and the septum primum and septum secundum. Because that's, it's so easy to confuse people when it comes to that in a question.
All right, let's just review these weeks anyways. This is an easy question, but...
Are you ready?
Yeah. Okay, I have a cardiology question 35. Children with trisomy 21 are at increased risk for endocardial cushion defects, a problem with the formation of atrial and ventricular septa. And so this will help us review the early cardiac development. At what embryonic week do the endocardial cushions come together to create the intracardiac septa? Is it A, week 4, B, week 8, C, week 10, D, week 16, or E, week 20?
All right, I guess I have to take this on. Well, the good thing is that Rooney just explained to us this week that the heart should be functional by week 8. So week 10, week 16, week 20, I'm going to remove. The question is it week 4 or week 8? And I do feel like this is sort of part of the later stage of heart development. So I'm going to go week 8. Daphne, are you there?
So you said week 8.
Yeah.
Okay, that's right. Answer choice B. Cardiogenesis begins in the 5th week of gestation with the formation of paired heart tubes. The tubes fuse and fold shortly after, much like Rooney described. The heart begins to beat during the 6th week of gestation, and septation occurs between embryonic weeks 7 and 8.
All right. Well, it's the least I could do. You know, if my medical students who I teach embryology to, I get the embryology question wrong. That'd be pretty bad. Daphne, Rooney, thank you both very much. We'll see you all tomorrow.
Thank you, guys.
No goodbye from Daphne. That's okay.
Oh.